You ever wonder why your hot coffee always gets cold, but never, ever spontaneously heats itself back up? Or why it's so easy for things to fall apart, but so hard to build them? Well, the answers aren't in some self-help book. They're baked into the fundamental laws of the universe, the laws of thermodynamics. And today, we're going to decode these unbreakable rules that govern absolutely everything. All right, let's just dive right in with a super simple question that, believe it or not, hides a deep cosmic truth. Why can't you unscramble an egg? I mean, once it's cooked, it's cooked. There's no going back. And this isn't just some, kitchen curiosity. It's a really profound puzzle. And the answer, believe it or not, starts at a level you can't even see. It starts with the frantic, chaotic dance of trillions upon trillions of tiny particles. To understand why eggs don't unscramble, we have to look at the very foundation where the rules of the entire universe are written. So, to really get a handle on the big picture, we first have to zoom way, way in. We need to meet the players in this cosmic game, the molecules themselves. So, what is temperature really? It's not some abstract thing. It's actually just a measure of how fast molecules are moving around. When we say something is hot, all we're really saying is its molecules are zipping and vibrating with a ton of energy. And cold? Well, that just means they've slowed way down. It's all about motion. So when you add heat to something, anything, you're literally just pumping energy directly into its molecules. And all that extra energy makes them move faster and faster, which increases what physicists call the system's internal energy. It's just the grand total of all that microscopic wiggling and bouncing. Okay, so we've met the players. Now it's time to learn the first rule of the game. And it's often boiled down to something like this. In the great game of energy, you can't win. Period. There are just no free lunches. This is it, the first law of thermodynamics. You can think of it as the universe's ultimate accounting principle. Energy is like this cosmic currency, and the total amount in the universe is fixed. You can't just make it out of thin air, and you can't destroy it. All you can do is change its form or move it from one place to another. The best way to think about this is like a super simple budget. The internal energy of a system is like the money you have in a bank account. Adding heat, that's a deposit. Making the system do some work, that's a withdrawal. And the books always have to balance. So what does work actually mean here? Well, a classic steam engine is the perfect example. You add heat to water, you get this super high energy steam, and that expanding gas goes and does work by pushing a piston. That's a direct conversion of thermal energy into useful mechanical motion. That's the energy withdrawal in action. But here's the thing. The first law? It isn't the whole story, not even close. It tells us the books have to balance, sure, but it doesn't tell us which way the transactions are allowed to flow. For that, we need Rule 2, the law that explains why, well, things fall apart. And this is why the second law is so important. According to the first law alone, a puddle of water could just spontaneously freeze on a hot day and make the sidewalk even hotter. The energy would balance out, so the first law would be totally fine with it. But we know, you and I both know, that's just nuts. It never happens. And that's because reality is governed by the second law, which tells us the direction of energy flow. Heat naturally moves from hot to cold, not the other way around. The concept that explains this direction is called entropy. Honestly, the easiest way to think about it is as a measure of, well, messiness or randomness. Your bedroom, right? It's got low entropy when it's all neat and tidy, and high entropy when it's a total disaster. And unless you put in the work to clean it, which way does it always go? Towards the mess. Well, guess what? The universe works the exact same way. And that brings us to the core of the second law. In any natural process, the total messiness of the universe goes up. Always. It is a one-way street, from order to disorder. This is the law that tells us why you can't unscramble an egg. So, okay, the universe is always tending towards chaos. But here's what's incredible. We've actually figured out how to harness this tendency to build our entire modern world. Let's take a look at engines and refrigerators. This is a really key way of looking at the second law. And it's the second part of our little energy game analogy. Not only can you not win, you can't even break even. No engine can ever be 100% efficient. There's always an energy tax you have to pay, and it usually comes out as waste heat. Every single heat engine, the one in your car, the ones in a massive power plant, they all work on this exact same principle. It taps into the natural flow of heat, from a hot source to a cold place, a cold sink. It siphons off some of that energy to do work, but it must dump the rest as waste heat into that cold sink. It has no other choice. You see, an engine and a refrigerator are really just two sides of the same thermodynamic coin. An engine exploits a natural flow of heat to get work out of it. A refrigerator does the exact opposite. It uses work, electricity from the wall, to force heat to go against its natural tendency, pumping it from the cold inside of the fridge out into the warmer air of your kitchen. Okay, so we've gone from tiny molecules all the way to engines. Now let's just zoom all the way out and see what these unbreakable rules mean for time itself and for the ultimate fate of the entire universe. This is, hands down, one of the most mind-bending and profound ideas in all of physics. Entropy is the arrow of time. The reason we experience time flowing in only one direction, the reason we can remember the past but not the future, is all because of entropy. The universe as a whole is moving from a state of lower entropy to higher entropy, and that relentless one-way march toward disorder is what we actually perceive as the passage of time. And if you state this law in cosmic terms, it is absolutely unbreakable. For any single process that happens anywhere in the universe, the total entropy either ticks upward a little bit, or at the very best, it stays the same. It never, ever goes down. It's like the universe is keeping score, and the disorder score is always, always rising. Now, if you follow this law all the way to its logical, ultimate conclusion, you end up with a pretty wild concept called the heat death of the universe. It's a state in the far, far, far future where everything is the exact same temperature. All the energy will be perfectly spread out, completely disordered, which means no heat can flow, and therefore no useful work can ever be done again. Just a quiet, final equilibrium. And that leaves us with one last, just fascinating thought to chew on. In a universe that is on this relentless, unavoidable march towards total disorder and chaos, then how in the world do you explain the existence of something as incredibly complex, as beautifully structured, and as exquisitely ordered as life, as us? That's a question the laws of energy force us to ask.